Okay, let's walk through the growth rate exploration. So, hopefully at this point you've already done some exponentials from last week, and hopefully you're okay with the idea that we're going to use function notation and plug in x values and get out f of x values, which will correspond to y values, right? And so um, I was thinking about, well, we could move forward with, I could just give you growth rate and make you do a bunch of graphing, and then we can move on to something else like logs or something like that, that for many of you guys is not going to be super valuable, especially in the short term. And instead, I decided to kind of stop and focus on exponentials and look at a specific use for them in talking about growth rate, because I think that that's something that a lot of us can relate to. And looking at growth rate, especially now, this first example with COVID-19 deaths is hopefully something that's relevant and something that is mildly interesting. And so I decided to stop here and kind of look at this for a little bit. And um, if you're listening to this on Friday or beyond, then there's a chance for you to build your own growth rate model, and that will be the assignment for Friday. So do take a look at that. But it's going to lean heavily on this, so it's important that you do understand what's going on here, right? So um, let's kind of go through the assignment, and hopefully it'll all start to make a little bit more sense. So using the idea of COVID-19 and its growth, I think a lot of us can relate to that, because especially for January and February and March, we were seeing quite a few different projections, models, formulas, however you want to think about that. And the thing that makes that tough is that um, one, different people are going to show symptoms. Some people may show symptoms. Obviously, if you've heard that a lot of people do get it and don't show symptoms, they're kind of these silent carriers and they have no clue. We also know that there's people getting healthy, and there are a lot of people that may be sick but don't report it. And it's tough to say, oh, did someone die from COVID-19, or did there's some people that are in poor health, and did they die from something else? And so there's a lot of different factors that causes our models to vary. One of those factors that we can kind of look at through this assignment is that if we don't have a high sample size, then it's very tough to come up with an accurate model. And so you'll see, hopefully, that it's important that we have large numbers of data, so that when we go to make a model, it isn't there's not a high level of variance. It's not varying a lot. So um, the idea here is that taking an exponential, so remember the general formula is ab to the x, we can take that and modify it to think about it in terms of percent growth. So basically, if I'm looking at f of x equals 2 to the x here, that is 100% growth rate, right? And the reason that is because if I think about it, oopsies, think about it like this. Right? What's happening is I'm kind of repeating this one, and then I'm doubling it. So I'm kind of adding on another one each time. And so I have 100% growth rate. Alternatively, a 0% growth rate is just f of x equals 1 to the x, which is the same as 1 plus 0, right? So we're repeating what we started with each time, whether that's each day, each year, each month, each week, whatever our period is that we're choosing to look at this over. But it's not growing, right? This second number here is what we call the growth rate number, and we'll look at that more. But the 0% and 100%, the gap between is not very big, right? It's 1 to the x and 2 to the x. And so we want to kind of figure out, okay, first step is to look at some data and decide what's a good growth rate, right? Is it 10%? Is it 15%? Is it 40%? Is it 50%? God forbid, is it 100%, right? And so our goal is to kind of look at that. So part one here, all you're doing is just seeing what that looks like, right? So if I say, how many cases are there on day one? Then you take g of x and you evaluate it at 1. So 1 to the 1 would just be 1. So there's one case on day 1. And then to find day 15, g of 15, which is 1 to the 15th. And you get something out, and that's how many cases, and then you do it on 33. I know 33 seems a little arbitrary, but that'll make a little bit more sense, hopefully, when you go to number 2 here. Okay, and so when I say does it accurately represent the spread of a highly infectious disease, just think about what you've seen with the coronavirus pandemic so far, right? Are the cases, are deaths, the total number of deaths doubling every day? Is it 200,000 one day and then 400,000 the next? Does it stay the same? Is it 200,000 and then 200,000 and then 200,000? I don't think either of those is necessarily right, so I'm guessing that we're looking for something that's somewhere in between 0 and 100%. And part one, the goal of part one is to get you to kind of think about that. Hopefully you'll notice that 0% seems too low and 100% seems too high, right? So let's kind of get into building the model. So I found this website. It's called Our World in Data, and if you have any interest in looking into, they have a bunch of different data on a lot of different things worldwide, whether it's pandemic stuff or wars or all sorts of different historical data. It's kind of an interesting place to look. But I went there, and the data that I was most easily able to find in terms of our current pandemic is that the data for total number of deaths on a worldwide basis. So that's what I decided to go with, and we're going to try and build a model to do that. So the first step is to find a growth rate, right? And so a growth rate is looking at, in this case, we're going to say from one day to the next, how many more death cases do we have compared to the previous day, right? And so that'll give us our growth rate. So the first day, we want to look at the growth rate between 2 days. So you'll notice that I paired up the days in twos. So we've got the 10th and 11th day. This is days since January 11th, and that is just because that's the first reported date. Obviously, we don't know for sure, but I did these in pairs. So each one of those I'm using to find a specific growth rate, right? And to do that, I take one day and I divide it by the total number of cases the previous day. So I take 17 divided by 6, which is 2.833, right? And to get a percentage out of that, I want to subtract 1. So 2.888 divided, or 2.833 minus 1 is 1.833, and then we multiply it by 100 to get a percent, which is 183%, right? So that's a massive growth rate. That's almost tripling every day. If we're tripling every day, then one day we've got, 200,000 deaths, and the next day we have 600,000 deaths, and then we have 1.8 million deaths. And so you can see how that growth rate seems a little bit high, and not even a little bit, just extremely high. And the reason that is because we have such a small number there. So from one day to the next, yeah, maybe we do have 7 more deaths, but there's, that's, if you think about it just in terms of numbers, in April, there were days where there were 20,000 deaths worldwide, and still the growth rate is not near what it is here. So when we have small numbers, the growth rate can kind of seem inflated above what it might truly be, right? And that's why we're looking at a bunch of different days throughout the course of the disease so we can kind of see how that growth rate seems to develop. Okay, so January 21st and 22nd, the growth rate was 183%. I can do the same thing for February 22nd and 21st, and we compute that and we get a growth rate of 4.98%, right? So if you just look at these two numbers, it looks like the death rate went down 179%, 178%. That's awesome. We did really well. But if you look at just the numbers, oh, well, there was actually about 100 more deaths between those 2 days. So is it really that much better, right? We had 11 deaths between the first 2 days, and now we had 100. Well, that's something to kind of ponder and think about on your own, and maybe it's not super math related, but that is kind of an interesting idea when it comes to thinking about something like this. If we look at the next 2 days, almost 1,700 more deaths. That growth rate is quite a bit bigger, 15.11%. And we look at April or 21st and 22nd, so pretty recently, about a week ago, our growth rate was back to around 4%. Right? So you can see there's quite a bit of variation between these 8 random dates that I picked, right? We saw as low as 4%, we saw as high as 183%. Maybe if we were kind of cheeky, we could get rid of that 183% and kind of focus in here and say, well, it's got to be somewhere in there, right? Maybe it's between 4 and 15, and we want to figure that out. I decided to also give you a little bit more data. This data is a little bit tougher to find, so I decided to give it to you guys, and that is that the growth rate for April was between 5 and 6%, and for March it was between 8 and 9%. So it might be valuable to write that, we've 6%, maybe around 9%. We've kind of got a variety of numbers to look at here, right? And so this is where it kind of departs from what you guys are kind of used to in math, where it's rigorous and there's a right answer every time. When you're building a model like this, there's just not a right answer. There's answers that are more right and make more sense, but there's truly not just right and wrong answers, right? And so this is where it's nice to kind of understand the data and think about the problem a little bit, and then you get to choose your own. So with the problem on Friday that I give you, you get to pick your own growth rate. I'm not going to tell you what to do. I'm going to give you some data, and you'll find some growth rates, and then it'll be up to you to decide, well, I think that, 8% is a reasonable growth rate, or I think that 20% is a reasonable growth rate, right? And all I ask that you do is you justify that. You say, well, based on the data, I think that it's this because I think that the rate's going to continue to grow, or I think 8% because that's in the middle of all the percents we've seen, right? And there's a variety of different ways to go about it, and part of that is just understanding the problem as a whole. So that being said, I decided that I was going to go with a growth rate of about 7% for the COVID death rate, and nothing special about that. Just when I look at the data, to me, 7% pops out as something that's not too conservative, but it's also not something that is going to make people panic because it's so high, right? And so that's why I decided to go with 7. You could have just as easily gone with 5%. You could have gone with 10%. If either one of those feels better to you, then I encourage you to go about using that. I just chose to use this because 7% made sense to me. Right? So that's the bulk of the work. That's the bulk of the thinking, the logical part. Now we're just going to plug it in and use it. Okay? So if we look at our exponential formula, it was a plus bx, a times b raised to the x. Really, all we're going to do to change that is we're going to kind of make b into, we're going to separate out b. We're going to expand it, okay? And so a stays the same. we're still raising it to the x, but b is now 1 plus r over 100, right? And so what 1 is, and 1 is our just what we had from the previous day carrying that number over, right? So if I said the total deaths on April 21st is 170,000, and then on the 22nd it's 177,000, then that one that I'm adding up front accounts for those 170,000 deaths, and then my 7% growth rate will account for the 7,000 deaths that occurred between April 21st and April 22nd, right? So those additional deaths, that's what the R plus 100 takes care of, right? And so the R plus 100 is just my growth rate as a percent. So in this case, it's 7%, and then I'm dividing it by 100 because I want to put it into decimal form so that I can kind of operate with it, right? So A is going to be that starting number of deaths. So if we're starting our model at January 11th, then the starting number of deaths is just 1, right? There's been 1 death that's happened, and if we're choosing to start it later on, then we would use however many deaths there are on that date and then build off of that with our model. R is the growth rate. So from one day to the next, how does our total number of deaths increase? And X is how many days since we started our model. So whenever we choose to do that, that's what X is going to represent, right? So you'll see here with this first example, if I have a growth rate of 100%, then that's that 1 plus 1. So it's whatever was the previous day, and then I'm doubling that. I have another set of that. So if I had 2 cookies and the growth rate is 100%, and the next day I have 4 cookies, and then the next day I have 8 cookies because it's 100% every day. I have 100% of the previous day, like twice, and it's a kind of a strange concept to think about. But growth rate only accounts for extra growth on top of what we previously had, right? Alternatively, a 0% growth rate would be we have what we had the previous day, and we'll continue to have that. It'll be if we have 100 cookies, then we have 100, and we have 100, and we have 100, and every day we're going to have 100 because nobody's eating them and nobody's making any more. It's going to stay exactly the same. The growth rate is 0%. And hopefully that makes a little bit of sense. So using our growth rate, which we decided was going to be 7%, I plug that into this formula. 7% divided by 100 is 0.07, and 1 plus 0.07 is 1.07. So that means that this here is our first draft of the model, right? Now we would be maybe it wouldn't be very thorough to make a model and then not test it to see how it works, right? And so we already have data, so we may as well try it out and see how well it fits that data, okay? So on April 22nd, that was day 102. So we're starting the model on January 11th, so we want to plug in day 102, which would be X is 102. So I evaluate that. 1.07 raised to the 102nd power is 903.45, but we can't have partial people, so 903 deaths, okay? If we go back, way off. We know for sure that the data tells us that there was 177 deaths by April 22nd, right? So clearly there's something wrong with our model, okay? Why is that the case? Well, we talked about it briefly, right? Where at the beginning, our growth rate was originally 183%. And the reason that is because we can't have half people, right? So if you do our growth rate of 7%, for the first 9 days, we don't even make it to 2 people. It's like 1.1 people are dead, and 1.2 people, 1.3 people, 1.4 people. But we can't have half people, right? There's either 1 person dead, or there's 2 people dead, or maybe there's more. But those first few days, our growth rate is very difficult to establish because there's a high level of variation because we are looking at a very small sample size, right? Now, one way to go about kind of getting rid of this fallacy, this issue with our model, is if we start our model on a later date. So January and February, there were a lot of people getting COVID, but not a lot of people dying yet, right? We had small numbers of people, and so there was high variation in our growth rates. But by beginning of March, we were starting to get kind of enough people to establish, okay, from one day to the next, this is kind of what we can expect as a growth rate, right? So instead of starting our model on January 11th, I'm going to come a month and a half later to March 1st. And on March 1st, there were 2,900 deaths. And so instead, our starting value, which was previously 1, we were starting on January 11th when there was 1 death. Now we want to start on March 1st. There was 2,979 deaths. So we're going to change our A value for that, keep the growth rate and everything else the same. And if I once again check March 22nd, which is now the 60th day of our model, just because we moved it up, we get that there should have been 172,000 deaths. And if you look, we had 177. This is a lot closer, right? Our margin for error is a little bit smaller, quite a bit smaller actually. You may say that growth rate wasn't quite accurate, right? And that's okay because it's a model. It doesn't have to be perfect. Maybe you would say, well, I think that maybe we should have gone with 7.5%. Maybe you're right. Maybe that should have been what it was. But we can hopefully see that 7% at least gave us a general idea of what we can expect. And hopefully you can see a little bit better how models would change over time as we get more data and as those growth rates change and as different variables have different effects on death rates and people being infected and that sort of thing, right? If a bunch of really young people are getting infected with healthy immune systems, then that death rate could be really low. But if it hits a community where there's a large majority of elderly folk, we may see that death rate go up, right? And so being able to account for different factors like that is kind of why we have people whose jobs it is to look at all of those factors and adjust the growth rate based on those sorts of things. And so what we did here is just a basic guess, but you can see that it was relatively accurate. And that's one of the cool things about math is we are able to kind of make accurate predictions about data and about numbers and about things that we can expect to happen. Okay, so that being said, our final model is going to be 2,979 times 1.07 to the x. And this is a model that starts on March 1st. And so March 2nd would be day 1, and March 3rd would be day 2. It's days since March 1st, right? And that's our x value that we're plugging in. Now, great that we have a model, but not really useful if we can't explain it or understand what our issues with it is, right? If I just have a model and I say, this is the model, and you either agree with it or you don't, that's not a very good way to communicate. We want to be able to understand what's wrong with our model and what's good about it so that we can have those discussions with people about it. And so that's what part 2 is meant to be. In part 1, right, we want to talk about why the models varied a lot. So I talked about quite a few different variables that there could be, and I just want you to reiterate that, right? Discuss it, put it in your own words. Tell me a few sentences about what's going on. Why is important that we take into account that there is high variation when numbers are small, that sort of thing. Number 2, it is just maybe another person looks at the data and says, well, I think that 8.5% is a accurate growth rate. Maybe it is, maybe it's not. Your job is to say it is good for this reason and it's not good for this reason, right? Maybe you think it's too high, maybe you think it's too low, but you give me one reason that you think it is a reasonable growth rate and then one reason that you think it is not, and explain it a little bit, right? You're trying to explain yourself as to why you think it is or it is not. This is kind of the important pieces of what we learn in math, is to be able to critique and critically think about things. And so this is maybe one of the more important things that you'll learn in a high school math class, right? Um, Last one, number 3, just kind of a personal question. Do you think that March 1st was a good time to start the model? Would you have wanted to start it later? Would you have wanted to start it earlier? Once again, no right answer. This is just you being able to justify yourself as to why you think you should start at a certain time or not. Maybe you look at the data and you said March 1st is too early, 3,000 is not that big of a number. I think we should have started it later, and perhaps you're right, right? The last one is just preparation for Friday. I want you to look at one specific, to quickly build your own growth rate formula. So I gave you the growth rate and I gave you your A value, right? And so I just want you to plug it in to our formula, which was right here. So A is that starting number of deaths, R is that growth rate, and then to plug it in and simplify. And then I want you to figure out how many deaths there are on the day. So today is May 1st, at least when I'm recording this. So that would mean that it's been 31 days since April 1st. And so I would plug in 31 as my X value and see how well that matched the number of cases that we currently have, right? The last thing is looking at your model. Is the current number of cases in the US higher or lower than what your model says? And what does that indicate to you? Does it seem like the pandemic is speeding up? Is it slowing down? There's, almost 8 billion people in the world. Is it going to hit all of us? Is it going to continue to ramp up until we all have it? Or does it look like it's slowing down? Does it look like these quarantining measures have had some sort of positive effect? And so I would like for you guys to look at that. So that is kind of my annotation of the assignment. I know it was probably a little bit long, but hopefully you found it helpful. Hopefully you found it interesting. If you have more questions, do reach out via email if you need a specific piece explained. That's awesome. I'd love to hear from you. And hopefully you guys are enjoying this assignment, or at least finding it a little bit interesting. So that being said, hope you all have a good weekend. Hope you're all staying healthy and well and getting outside to enjoy the beautiful weather.